Welcome to AI for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you very much, Anna. Welcome everyone to today's session, to today's talk, Explainable AI in Cases You Cannot Spot the Dogs or Cats by Alexander Binder. Professor Alexander Binder is Professor for Multimodal Machine Learning at Leipzig University, Principal Investigator at the Center for Scalable Data Analytics and Artificial Intelligence, the SCADS.AI, Dresden-Leipzig, and member of the Alice Unit Jena. His research focuses on the explainability of complex AI systems, in particular multimodal models that integrate diverse data types such as text, images, audio, and sensor data. Binder's work addresses a central challenge of modern AI, understanding how and why models make decisions. His research explores non-causal correlations, adversarial vulnerabilities, and hallucinations, aiming to develop more transparent, robust, and trustworthy AI. He studied mathematics at Humboldt University of Berlin and received his PhD in computer science from TU Berlin in 2013 under Klaus Robert Müller, co-developing layer-wise relevance propagation, LRP. After positions in Oslo, he was assistant professor at the Singapore University of Technology and Design and later associate professor at the Singapore Institute of Technology. Now, Professor Binder is at Leipzig University and he's building a research group focused on explainable and multimodal AI. I'm very excited to give the floor to Professor Binder and hear more about his work.
Thank you very much. Yes, let me share the screen and then open that, and that should now work. Okay. So thank you for introducing me again. This is the title of the talk, and maybe let's start with it. So you may ask yourself, of course, to what extent is explainable AI useful? And for example, you take a neural network. So I started my work a lot in vision and, something whatever like a ResNet or if an efficient net or transformer, then you implement a method to compute an attribution map. You compute an attribution map, you're super happy, and then, you code it a lot, and somebody asks, then something like, yeah, and now, so what? What is it good for? Otherwise, it's producing just nice pictures of things that you anyway knew where they should be. So I worked on these and that problems, and I want to show you that from my own personal experience, explainable AI also works in cases where you cannot eyeball the ground truth easily. However, you need to think how to design an XAI unrelated or task-dependent validation. So I'll go on 2 papers for this in the next half an hour. This is Explainable AI for channel selection for pruning. This is a paper by Seol-Ki Yom. It's called Pruning by Explaining from 2021. And a bit of newer work where we did not know what visual evidence would be a priori. This is Schöpert and Nature Scientific Reports. And when you see the pictures of the second paper, the data, you will get an idea what I'm talking about when you cannot see the dogs or cats in that. Okay, so the first thing is, identifying channels and feature spaces without the ground truth. And this is Explainable AI for neural network pruning. Why would one do this? So I give you, for example, an architecture. This is a vision network. They are simpler to explain. This is, for example, a ResNet 50. And if you look at this, you have here 64 channels, 256 channels, and you have 3 blocks of those. And then you have, one more block, one more block, one more block. And you have, in principle, you have thousands of channels in this. And each channel is, in principle, for a CNN. It's the output of a convolutional pattern detector. And if you take a pre-trained vision neural network and you fine-tune this on a smaller target data set, then not all channels, do something meaningful, and you can prune them away for improved compute efficiency. So this is the one part of AI for good in principle. If you prune away channels, you make this thing lighter, you use less electricity, and this is also then, less inference costs in the end. Of course, not all channels you want to remove. So this is an example where I fine-tuned a neural network on Pascal VOC, and I just looked at one particular channel from one particular layer. And then I explained what this channel actually was firing on, and you see this channel has encoded, obviously, bus fronts with windows. So this is something that if you want to use the neural networks for buses, you don't want to remove. How can we use Explainable AI for pruning? The idea is very forward. So I take an image and I do a forward propagation, okay? Then I do a modified backward pass. And the modified backward pass in principle gets me some relevance scores for every neuron and for every channel, indicating how important is this neuron or channel for this particular image. Then I do this in principle on a few images and I get an average relevance for every neuron or channel. And then I can just remove those channels that have in absolute values the smallest values. So I keep those channels that have high positive, and I keep those channels that have high negative relevance. Also good. And when we try this out, first we try this on some toy data. So you have here, it's like experiments by Sebastian. We had some, in principle, toy classification problems. This was just the first visualizer in principle. 2 class, 3 class. And then you use a few reference samples, 2 times 5, to compute your neural network statistics for pruning. And then you have several criteria, and you can compare to the original ground truth decision boundary how good these methods preserve. Okay, using Explainable AI works in principle. Then we did this in principle. We just repeated this experiments a few hundred times over the redrawing of these artificial data sets. And then we asked ourselves again, if you use, for example, 5 images per class and you do pruning, how good perform the methods in principle? How much do they retain of the neural network's accuracy after pruning? And you see the red line is LRP. And it works reasonably well, but weight-based pruning is also actually in many cases very, very good. So for more than 5 samples, proper LRP, not epsilon, but epsilon beta, like this works well. Then next we went to ImageNet pre-trained networks. And first experiment is you prune and then you do fine-tuning on your target domain data after pruning. So if I first prune, then I do a fine-tuning, I can heal damage caused by pruning methods. So this requires more data, but it's also more robust. And then we run experiments on several fine-tuning data sets, including cats and dogs. And we just asked ourselves in principle, when we prune in principle 10%, 20%, 30%, and so on, 40%, 50% of the channels, how does actually our performance behave? Yeah, here's the red line is again LRP. Yeah, and we see on some data sets with pruning after fine-tuning, explainable AI has a small edge. On Cypher 10, everything is the same. Yeah, if your data is too simple, then all the simple methods work, and you usually see that weight-based criterion is in principle a good baseline. Good. Next, for just showing the difference in these pruning methods, we went for pruning without fine-tuning. So pruning without fine-tuning a prune, and any damage that left by suboptimal pruning just stays on. There is no safety net, like in this example here. So I can't undo the damage from bad pruning. And I did this here for an example for a ResNet 50. And I, in principle, created artificial binary classification problems. This is airplanes versus birds. Yeah, this is airplanes versus cars. This is cars versus birds. And again, I run different criteria. We prune certain percent of filters, and we see what is, in principle, your test performance after pruning. And here, where you don't do fine-tuning to heal the damage, then the difference shows stronger. And gradient and Taylor-based criterion, they lose quite fast out. Weight-based pruning is much more robust. LRP-based pruning is even more robust than that. So the point is, yes, you can use this. This, of course, Vision Networks is experiments in 2021. But this is something that I keep in mind when I may want to, revisit this for, in principle, large language models. So point is, yes, explainable AI is useful also in absence of domain knowledge. When you cannot just visually, just check that it, aligns with what you expect them to happen. Okay. This was one of the papers. Let's look at something newer. This is Shilp et al. And Nature Scientific Reports. And this is called Deep Learning for Predicting Stem Cell Efficiency for Use in Beta Cell Differentiation. So I was more on the computer science side, but beta cells are in principle, cells that should be able to produce insulin in principle. And, the idea is that at some point you hopefully could implant differentiated stem cells into beta cells, that you could implant them in patients that they produce insulins. And the question for this data is, you have cell cultures and you ask yourself, do they differentiate properly or not? And I can zoom in into the data. I just zoom in here for fun. This is after 0 hours, after 24 hours, after 48 hours, 53 hours, 72 hours. If you look at this, the blue is a good clone, the red is a bad clone. And if you look at this, you don't see much. I can see something like an HE stain of breast cancer. 99% of the case, I can see what is breast cancer cells. But this is something unstained. You can't see what's going on. This was something where there was no visual prior existing. And then at first, we just trained neural networks to see what is the pure predictive accuracy. That was the first question. And actually, when I saw the images, I expected, okay, we'll have maybe 55, 60% accuracy. This will work somewhat, but not very good. Then I looked at accuracy results, and there's patch level accuracy and there's clone level accuracy. Clone level is in principle, I take all the patches of a clone and I average the prediction to get in principle clone level vote, where the patch level errors hopefully cancel out. And of course, I just tried also something like logistic regression, something like this on plain images. This doesn't work. Transformers didn't work too well on this data. ResNet 50 worked better. Wide ResNet 101 worked even better, and EfficientNet V2S worked even much better. And at the point, it was clearly over the 50%. This is a balanced data set. If you just do guessing, you land at 50%, or if you're unlucky, below 50. And this was a little bit shocking. So for 6 cell lines. And then the first thing is I was just bothering the first author and the medical people, is there some bias from uneven lighting in this a chamber or something like this? Or so, I mean, we also did exclude bad data split design. We didn't split the clone into train, while, and test. So, and when we had excluded biases, then it looked like there is a structure, but we looked at the cells, there's nothing humanly visible. And then we pulled out LRP to look at the explanations, and then we saw something. So this is an explanation for good differentiation, and blue is evidence against it. And blue evidence against it is here in a zone where there is a hole. There are no cells. Again, here, also prediction for good differentiation. So blue is evidence against it. There are, in principle, blue spots where you have a hole between cells. And again, the same thing, another style. Here are the holes. Here's the evidence, again, good differentiation. And then we saw that the neural network actually saw some structure, even if its structure means the absence of something. And that was something that we had an idea, okay, now we know what's going on. Your other example where I have prediction for poor differentiation, then red is evidence for poor differentiation, but you would see in principle similar pattern, and this was in principle just epsilon, beta, LRP, so epsilon for the top layer and beta for all the other layers. And so why LRP? Well, if I do this, for example, with smooth gradient times input, var grad, I just looked at this, you don't see much structure in there. So there's just a bit too much noise for that. So this is the reason why we just went for LRP. But in the end, in principle, we were able to, being able to predict whether cell lines differentiate well relatively early. This was in principle a good result. So something that hopefully helps to increase the efficiency of, in principle, culturing these cell lines. And now you may ask yourself why we didn't stain stuff. The cell culture's on a flask. You don't want to open the flask, because when you open the flask, stuff can fly in, then fungi can grow or bacteria, but usually it's fungi. I mean, maybe you remember the story of the Petri dish of Alexander Fleming when he saw those fungi and on the bacteria culture, stuff like this. That was the reason actually why we didn't go for specific staining, because you didn't want to sacrifice any cells, you didn't want to open flasks. This is actually the technical reason for that. So now the question is, why does this stuff work? Very, very quickly, maybe. This is low-level attribution-based explainability. Of course, there are concept discovery methods and things like this, but in these use cases, it was the low-level stuff that mattered. And the idea is, in principle, I have a prediction on a sample, and the sample is a vector. And I want to decompose it in one score per dimension. And of course, this equation is under constraint. And the constraint comes from the many, many different ways to explain stuff, for example, from Shapley or gradient times input or smooth grad or LRP or GradCam. They all bring their explicit constraints. And for example, if you have tabular data, then you are very, very happy with using Shapley as it is. Here may be another quick overview how I see these low-level methods. They're forward pass based, they're backward pass based ones. And many of the forward pass based is, the idea is of you mask inputs, so you have some kind of a discrete input perturbation. And this is Shapley, this is occlusion, this is Rice. And then, of course, stuff like variants of Shapley, like kernel Shap and grad Shap and things like that. This is where I'm seeing the big picture of those methods. And each of these methods has a drawback and a pain. For example, Shapley values has a very nice theoretical explanation. In principle, I measure the score over a subset when I omit the feature. Here I omit a J. and I have a weighted sum. Yeah. And the weighted sum is made in principle so that it becomes an expectation. It has very nice, good theoretical properties. Yeah. And it's very suitable for tree-type predictors when you can naturally just, deal with dropping features and then have missing features. But of course, what do you do when the predictor does not support missing features in the feature vector? I mean, for example, you have in a language, you have a sentence. I eat a tomato. If you drop the important verb, it becomes a very ambiguous sentence. Tomato, things like this. The other problem is, of course, that you need always to think about the scale of attribution that you want to measure. Things like a 1 pixel in a 4,000 times 3,000 image, changing that doesn't do any meaningful perturbation, of course. The other thing is, there are just data types where you don't know how to perform meaningful feature removal, and images is one of them. This is, by the way, for fun, Leopold von Sacher-Masoch. He wrote the novel Venus and Furs, and he was considered to be insane by his contemporaries. And how do I remove his eyes? This comes then back as a problem when you want actually to evaluate the quality of explainability methods. Here, maybe a quick overview over this. Now the next question is, what's the problem? Why did we use LRP for that stuff? Let me give you a very quick, not so mathematical, higher level explanation. So I have a prediction. I want to decompose it in scores for every dimension. And the prediction is now nonlinear. And if you want to decompose something nonlinear into a sum of scores, the first idea is, if you ask a mathematician, is to use Taylor expansion. One is you can choose a root. That matters a lot. But when I take a function, I approximate it around a point x0, and I have the value at x0 and the gradient times the inner product with the difference between the point I want to explain and my root point. I can write this out as a sum of our components. And now I have a sum of our components for dimensions. I can use this in principle as an explanation. This is very principled. In deep neural networks, this has one problem. That is noise. This is in principle a problem. So for example, here from the SmoothGrad paper by Smilkov et al., you take images, you run neural networks, and if you just look at the vanilla gradient, it has lots of gradient shattering noise. This is a little bit the problem with that. And many, many methods try to deal with that noise. Of course, now you can say, there is noise, but we train deep models using the gradients, and that works very good and very fine. What are you talking about for a problem? Well, then I will tell you, yes, you train with a gradient, but you use very large batch sizes to do so, to average the signal. To get a clean signal. I mean, contemporary training is what, 256 at least? If it's not 1024 or 4000 something. So you use super large batch sizes in SGD to get a large amount of averaging. The second issue, of course, with using naked gradient is gradient scales. Here, this is a part of the text from Joffe et al., the famous batch norm paper. And they wrote exactly why they use batch norm. If I use batch norm on something like weight of an input, and I take the derivative with respect to the input, it becomes, if you zoom in, it becomes invariant to the scale A of the weights. Batch norm achieves you scale invariance of the weights when you compute gradients and let them flow backwards. Scale of the gradients is another problem when you use gradients for anything. Good. And many methods somehow use denoising strategies. Now, just the last 5 minutes of the talk, how does layer-wise relevance propagation deal with that? And this is my own view. I mean, maybe Grégoire, Wojciech, Sebastian have a slightly different view. This is my own subjective view. Here, let me give you a very quick explanation. Maybe you know backpropagation. I have a neural network, and I use backpropagation to compute gradients. Actually, yeah, backpropagation is a way to realize chain rule along a graph. Yeah, and if I have here some inputs, I have an output of a neural network, then I have the intermediate neurons, then the intermediate neurons accumulate total derivatives, and along the edges, what is flowing backwards are partial derivatives. And if you write this up, you can write up actually chain rule in a graph-based way. This is what happens in backpropagation. You have total derivatives on the nodes, partial derivatives flowing backwards in the edges. LRP takes the same topological flow, just where backpropagation would have total derivatives, I have so-called relevances. Where you have partial derivatives flowing back along the edges, I have relevance messages flowing backwards. So LRP has the same flow along graphs as the gradients. This is the first thing. Now there are 2 components. I have a conservation property within a layer that places relevance scores on comparable scales. That's why I can prune different channels. And the second thing is many rules have a gradient clipping analogy interpretation. Many LRP rules. Very, very quick. Yeah, the conservation property within a layer is just the following, that if I have relevance messages flowing backwards from an output, they have to sum up to the relevance of the output. For example, the relevance of Y sums up to this message plus this message plus this message. The relevance of R1 is equal to this message plus this message. R2 is equal to this message plus this message. Very, very clear. And if you want to see how this is an action for conservation of non-trivial models, then see for example, the paper by Miss Jafari and this is published, I think, ICML NeurIPS 2025. Grégoire Montavon is also behind on this paper. If you want to see this, how this goes in practice. So this is the one thing. I have a conservation property within a layer. Scores become comparable, and things like pruning work then. Because I can compare relevances between different channels. The second thing is the gradient clipping analogy. So I show you this exemplary for LRP beta. You can show similar things under certain conditions for LRP gamma. So it's the following thing. This is LRP beta rule. I have a relevance from the output, and this is the relevance message from output neuron K to its input I. And I have here some funny terms. Note just this plus is just the positive part, minus here is just a negative part of a term. Now what I want to show you something very, very simple. For LRP beta, this term is bounded between 0 and 1 plus beta, because this is something positive to a sum of something positive where this one is included. It is between 0 and 1 plus beta when I multiply this with this. This term here, with this minus beta, this is a sum of negative parts of a ratio. This is between minus beta and 0. Point is, this is a kind of parametrized clipping of a modified gradient quantity that flows along an edge. So if this would be partial derivatives, this would be gradient clipping. Now this is LRP, so you can't call this gradient clipping, but this is the same thing. And clipping of gradients and learning signals is actually not that uncommon. There is this normalizer free nets paper. where they say, okay, I don't want to use batch normalization, so they have to use clipping instead. And reinforcement learning gradients and all other signals are clipped since people use that. I mean, if you look at the PPO paper, they clip something to be in a certain range, and this is then for reinforcement learning. Here, people are doing this in principle, for gradient-like terms to get in principle explanations that are somewhat more stable. This is all I wanted to talk. Let me end the presentation with saying, despite whatever you see in the news, there is still hope for this world. Thank you. I'm finished with my talk.
Thank you, Alexander. Are there any questions? Oh, Alexander, you can ask questions. I don't see any yet. Maybe they will pop up. Maybe I have a question more from the application side. Where would you see these models that are improved and fine-tuned, pruned? Where would you see the biggest advantage of using these models?
When you have domain-specific applications, I mean, sure, this is not something that you would use for ChatGPT, because ChatGPT is, the generalist for everything. Yeah, it should tell you some children's stories, it should tell you some jokes. But if you use something for specific domains, for example, for analysis of certain tables, or analysis of something like legal arguments, or of analysis of bills, there you don't need a model to be able to invent a children's story or tell a joke about your grandma or something like this. So for these specific things, and when you use them for inference, the model is 5% lighter. It consumes 5% energy less, which is good for the environment and good for your bank account.
Yeah. Great. So that is where there is still hope for this world also, in that sense. Yeah.
There is a question, right? What does LRP stand for again? Well, when we wrote the first paper, we need to have a name for the technique, and we called it layer-wise relevance propagation. And it's just the way of humorless Germans giving a paper title.
Okay. See whether there are other questions coming in. Good that you spotted it so quickly. Otherwise, I have another question also about the averaging. So does the domain specificity also help? Because usually this is in cases where there are not large batches of data? Or is that unrelated?
It might be unrelated. Of course, the pre-training of models usually comes with, you need large batch sizes. I think if you do fine-tuning, then probably smaller batch sizes should be okay. If it's how should I say, if the signal is clean enough. But generally, I mean, if you do gradient-based training, you use a big batch size, and this has, of course, a denoising property on the gradient.
Okay, so there's another question now from Lucia Gomez Tejero, where the frontier sits for explainability across NN types and language transformers.
I think there are good explanation methods for vision transformers. You can check, for example, the attention LRP. You can check the work of Leo Wolf and things like this. There was also a very nice last year ICML paper that I've seen that brought a new type of prior, and there are explanations for Mamba models. So I think the frontier is maybe in the interplay of multimodal models. I hope I'm not mistaken, but I don't. I'm not a tech evangelist, so I'm not good at making predictions.
Okay. Are there any other questions? Yeah, there is one. Was there a slide where the calculation of relevance was shown? Maybe someone missed it and is asking for it again.
This is an example for LRP beta relevance. For the top linear layer, one can just use a simple decomposition aka LRP epsilon, which I did not show, so I didn't want it to go too deep into math because I was not sure. Maybe you take a look, at the papers of Grégoire Montavon where they go into the theory. There is a newer paper by Leila Aras on efficient implementation that you might want to be interested in. So these are papers that I didn't co-author, so I'm not just trying to sell my papers, something like this. It's also interesting to check works on some other people. Leo Wolf, for example, comes also to my mind when I see this kind of literature. Yeah. This is LRP beta. There's also LRP gamma and stuff like this. Yeah. Okay.
Any other questions? Let's see whether always typing and putting it here takes some time. So let's see whether something is coming. If there are no further questions, maybe Alexander, is there anything that you want to highlight again as we have some time left, or
I don't know. I'm
maybe
happy.
you're happy. That's great. So there's no more questions. So maybe you can just repeat the key message to close it off.
I think
And
explainable AI can used also in cases where you cannot directly eyeball the ground truth. You need to think, of course, in one or another case, how do you validate it? But it is, I mean, it's the same thing as, for example, with any feature visualization technique. It's the same issue then.
yeah.
Also, when you use just T, S, and E, you need to see, are these clusters, just an artifact of my parameters, or can I validate them in a different way?
Okay. Great. So then if there's still no other urgent questions, then I would thank you very much, Alexander, for your talk. And I think then we can conclude this very interesting talk, giving some hope for the world. Thank you very much.
Have a nice day. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.